Hello, and welcome to Week 2 of Digital Integrated Circuit Design with Dr. Mark Narden. In the previous set of lectures last week, I went through the basics of CMOS logic, along with basics of how the CMOS, PMOS, and NMOS transistors function, and basics of fabrication technology. In this set of lectures this week, I'm going to introduce more complex logic, being able to explain the complementary nature of CMOS, which is complementary MOS design. Going into how to create and the functionality of more compound gates rather than just a simple single function like a NAND or a NOR function. How you can create gates that do multiple and or type functions all in one gate. Then going through passgate and tri-state logic, how they work, what the transistor connections look like for them, and how you can use passgate and tri-state logic to create multiplexers. And finally, going through the basics of sequential logic. Sequential logic is something that stores value of zeros and ones in a state and stores the value for a longer period of time. And we use latches and flip-flops as the main ways of doing our sequential logic. So before we start, let's do a quick mini quiz or activity, which is to sketch out what a 4-input CMOS NOR gate would look like at the transistor level. So I'll give you a little bit of time, pull out a sheet of paper. You can think about it in your brain if you can, keep up the complexity of that in nature. But let's pause for a second. Go ahead and pause this. I'll wait a sec for you to pause it and then start up again. So the NOR gate, 4 input, would mean that we need 4 NMOS devices, 4 PMOS devices. Since it's a NOR gate, the NMOS devices need to be ORed in their function, which requires you to have all 4 NMOS devices in parallel with each other. The inputs, the source and drains need to be connected together. All 4 NMOS sources are connected together to ground. All 4 NMOS drains are connected together to the output, and each of the gates is a different input, A, B, C, and D. For the complementary PMOS stack, instead of being in parallel, they need to be in series with each other. And so you would have the 4 PMOS in series with each other, with the top one connected to VDD, and then the source and drains are connected in, the drain of the first one is connected to the source of the second one, drain of the second one is connected to the source of the third one, down to the fourth. And then the output, the drain of the fourth one, would be connected to the output. So this is what it would look like. As I was saying it, you can see there's 4 NMOS devices connected in parallel, 4 PMOS devices connected in series. When any one of the inputs is high, it will disrupt this series PMOS stack and create an open. So if any one is high, there will be no connection to VDD, and if any one of them is high, it will create a connection for the NMOS transistor that's connected to ground. So A, B, C, or D, any one of them is high, and you get an output of 0. If all of them are low, the NMOS stack is completely cut off. You don't have any connection to ground. All 4 PMOS will be on if all of the inputs are low, and you will have a connection to VDD. The output will be a 1. And that would be a NOR function. So let's get into a little bit more detail about the complementary part of CMOS, again, complementary MOS logic gates. So complementary CMOS logic gates, you need a PMOS pull-up network, an NMOS pull-down network. And again, that, complementary MOS networks. Since those networks are complementary to each other, what that means is only one of those networks is on at a time. So either you have your PMOS pull-up network on and connected to output, and when it's on, the NMOS is off. And when the PMOS is off, the NMOS is on. You should never have a time where both of them are off or both of them are on. If you do, then it's not complementary. So you can see in the 2x2 chart here, the complementary nature means that if the pull down is on, the pull up needs to be off, and you're in the lower left quadrant of that 2x2 chart. And when the pull down is off, the pull up needs to be on, and you're in the upper right quadrant of that chart. So when your pull up is on, your output is a 1. When your pull down is on, your output is a 0. Now, if you don't have complementary logic, if you've done something wrong in your network and you don't have a complementary N and PMOS network, that means one of two things. Either both of your networks are off at some point. So if you have both your pull up off and your pull down off, that means you have no connection of your output to either VCC or ground. And your output is just going to float to some intermediate unknown value. And that is usually called a Z state. Sometimes people use Z for floating, sometimes they'll use X, which means unknown. But usually, if you actually have no driver, you should probably use a Z for floating. Typically the X stands for something that's unknown, but it's being driven to something, you just don't know what it is. Whereas a Z means you're not driving it to anything, and so you also don't know what it is, but it's not being driven at all. So the example of an X is in the lower right quadrant, where your pull up is on and your pull down is on. If you made a mistake and you have both of them on at the same time, that means that they're fighting each other. You're going to have some large amount of current, what's called a crowbar current, because you get current coming directly through the PMOS stack all the way through the NMOS stack from basically VDD to ground. You could get a very high amounts of current, potentially creating a fuse that winds up causing something to burn out, which is very bad. So usually you never want to do that. And that's denoted in this particular case in the lower right quadrant as an X value, because you don't know who's going to win between the pull up and pull down, whether it's going to be high or low or someplace in between. And again, creating a crowbar current is typically pretty bad. You don't want to do it. So try to avoid that in CMOS logic. So this slide here gives a good summary, as much as you can summarize, the behavior of series and parallel transistors. So if you're thinking about the behavior of series and parallel, we have series and parallel, both NMOS series and PMOS series, and NMOS parallel and PMOS parallel transistors. So that's the A, B, C, and D kind of rows that are shown here of the transistors and how they behave in the second rightmost part of the rows. So the thing to keep in mind is for NMOS transistors, if the input to the gate is 1 or a high value of VCC or voltage, the transistor will be on, and if the value is low or ground, the transistor will be off. But for PMOS, that's flipped. So for PMOS, if the input gate value is low, 0 or ground, then the PMOS will be on. and if the input gate is high or a 1, high voltage, the gate will be off and an open circuit. So if we take a look at each row one by one, row 1 or row A, where we have two series NMOS devices, if it goes through each of the combinations of the input gate value being 0, 0, 0, 1, 1, 0, or 1, 1. If you look at the first three values where the gates, any one of the inputs is a 0, the series devices will either both be open or one of the two of them will be open, and you get no connection to between the A and B, top and bottom of that stack. So you effectively have a connection that's off. There's an open circuit somewhere between A and B. And it's only if, for NMOS devices, both input gates are 1 or a high value of voltage, that you get a connection between A and B, and it's considered to be on. The connection between A and B is on. So for series NMOS devices, you need both inputs to be 1. The next row with PMOS devices, it's kind of flipped, because PMOS devices are on when the gate input is 0. So the very first selection where you have a 0, 0, you have your PMOSs on, and then the next three for PMOS in series are all off, because if any one of the input gates is a 1, so either a 0, 1, 1, 0, or both of them are 1, you have an open circuit. You don't have a connection between A and B, and the series stack is off. For the next two rows, we're talking about transistors in parallel. So in parallel, either one of them can be on. If either one is on, then you have a connection, and that connection is on. So for NMOS devices, if either gate is a 1, you have an on connection, and if both of them are 0, then you don't have a connection between A and B, as you can see. So if you have 0, 0 as your input, you have no connection between A and B. The overall combination gate stack is off. If you have a 0, 1, 1, 0, or 1, 1, all three of those are considered on, and you have a connection between A and B for the NMOS. And for the final PMOS in parallel, only if you have both inputs 0 are, or actually if any one of the inputs is 0, then it's on. So for the first three, where you either have a 0, 0, 0, 1, or 1, 0, there's, in each cases, the 0 will turn one of the transistors on, or both, and you get a connection between A and B. And only if both of them are 1, it turns off both transistors, and you have no connection, and you have an off. So let's take a more detailed look of one of our simplest complementary gate structures, which is a NAND gate. Keep in mind, if it's complementary CMOS or CMOS, the gates always produce at the output either a 1 or 0. You always have the N stack and the P stack. One of the two of them always have to be on, and either pulling the output down or pulling it up. So in this case, with NAND gate as our example, to get a NAND function, you need NMOS in series with each other. That gives you a AND/NAND function. So for a 2-input NAND gate, we have 2 series NMOS, and that produces a 0 at the output when both inputs are 1. So when we have both A and B are 1, high value voltage, they will turn the NMOS on. You have a path to ground, and you pull your input low. So in order to be complementary, what we need is if either input is low, so if A or B is a 0, since the NMOS stack will be off, that means we have to design the PMOS stack such that it will be on when either input is a 0. Because again, we need complementary. If we turn off the NMOS stack, we have to turn on the PMOS stack. So in order to guarantee that when either input is 0, we get a 1 out of the PMOS stack, that requires the PMOS to be in parallel with each other. So this brings us to the rule of conduction complements. If we have the pull-up network needs to be a complement of the pull-down network, that means any place we have NMOS transistors in series on the bottom, we need PMOS transistors to be in parallel on top, and vice versa, any place where we have NMOS transistors in series on the bottom, we need PMOS transistors to be in parallel on top. So in effect, your NMOS and PMOS stacks, you need to make sure series and parallel always flip with each other as you design them. So now that we've talked about some of the more basic logical functions we can do, let's talk about compound gates. This is a term for basically logic that does more than just a simple AND or OR function. In effect, compound gates can do any inverting function you want to design. It's just the more inputs you have, the more complex the pull-up and pull-down network is going to be. And if you have too many inputs, it might cause such a complex or too many gates to actually perform that function well, or in a usually you're concerned about the area of the gate as well as the how fast the gate can switch from an input switching to the output switching. If you get like too many inputs, like if you had 30 inputs, the gate might be so big and so slow that you actually wouldn't want to do that. But you in theory can do any inverting function you want to do. So let's talk about an example here. So the example is our output Y is equal to A and B NORed with C and D. Like I said, you can do any inverting function. So if I did A and B or C and D, that's not inverting. So if we have an inverting over the entire thing, then we can do that function in a single gate. So let's go through how we would create this. So in the A column, or A part of the figure, you can see you have A and B, so two NMOS devices in series with each other for A and B. And then you have the C and D part of two NMOS transistors in series with each other. And we said, well, we need to NOR those two things together. So that brings us to B. So we put those two stacks in parallel with each other instead of in series to get the NOR function. So that right there as our NMOS pull-down stack is the A and B NORed with the C and D. So that NMOS stack will produce that function. Now let's look at what PMOS stack do we need to pair that with in order to have a complementary logic function out of it. So as we said in the previous foil, any place where we had series before, we need to put it in parallel. So when we go to C, we look at the stack that we had from A. We used to have an A in series with B for the NMOS. That means we need a PMOS A in parallel with B. And likewise with C and D in series with each other, we need a C in parallel with D. So that gives us something that matches the PMOS now match the NMOS. That gives us the two separate logical functions for A and B there, and C and D. Now we need to put them together for the NOR function. You can see where with the B side we put the A and B in parallel with C and D. In this case we need the A and B parallel combination now in series with the C and D parallel combination. So we took those two sets of A and B parallel and C and D parallel, and we stack them on top of each other to put them in series with each other. And so that gives us our PMOS logic stack. Now we take those two logic stacks, we take the PMOS on top, we go to where the E figure is, part of the figure, and we have the PMOS logic on the top there, connected to VDD at the very top, and then we take the NMOS logic stack and put it on the bottom and connect them together where they meet, and then the NMOS is connected to ground, and the middle there is connected to our output Y, and that gives us our function A and B or C and D NORed together. And then the way that you could draw the symbol for that, rather than drawing out all the transistors independently, is you have basically something that looks like a NAND type gate and another NAND type gate just smushed together with A, B, C, and D connected to the two different NAND gates, and then and then a NOR gate at the output. So this is AND AB, ANDing CD, and then NORing those together gives us our output Y. So that shows us how we can create the transistor stacks for PMOS and NMOS, and what the symbol would look like that we would use in our schematics. So let's go through another example here. If you take out a sheet of paper, this might be possible to do in your head, but it's probably better to actually draw out because the connections, that way you can make sure that you actually draw out how all the different connections to the NMOS and PMOS transistors would be. So I'll give you a second to draw this out on a sheet of paper. And if you want to pause here while you draw it out, and then I'll talk about it after you draw it. Okay, so this is what the circuit would look like. So we have, in this case, A or B or C NANDed with D. So I typically always start with the NMOS stack, because the NMOS stack gives us the functionality in a little bit more directly when you're talking about ORing and ANDing as far as series and parallel. Depends on how you think about the logic, I suppose. So in my mind, I take the A, B, and C, which are all ORed together. So ORing A, B, C means for an NMOS stack, you're putting A, B, C in parallel with each other. So you should have 3 transistors at the very bottom, which are A, B, C, and then you're NORing that with D, which means the D needs, when you're doing an you're NANDing that with D. And when you're doing a NAND/AND function, that means it needs to be in series with the other thing. So the D transistor needs to be in series with the ABC parallel combination. Now, in theory, you could put D either above A, B, and C connected to the output, or you could put D below A, B, and C connected to ground. That's a little bit of a matter of choice. There's probably one is more ideal than the other. I'm not going to go into the details on that yet. We'll probably get into that a little bit more in future weeks. But here, just logically, you could do it either way. As far as the actual behavior in the actual layout and behavior of the cell, one way would be different than the other. So we've got the NMOS stack with A, B, and C in parallel with each other, and D in series with that combination. Now we need to create the PMOS stack. So we can take A, B, and C on the NMOS side, which are in parallel, and we need to create a series stack out of that in the PMOS side. So we have A, B, and C, you can see in series on the left-hand side on the top. And then since D was in series with A, B, and C on the NMOS side, it now needs to be in parallel with it on the PMOS side. And so we have A, B, and C in series with each other, and then connected in parallel with that entire stack, we have the D transistor connected to VCC and our output Y. And this gives us the logical function of A, B, C NORed together, and then NANDed with D. And of course you could draw a symbol related to this as well, where you might have a 3-input OR type gate with A, B, and C going into it, and then have that go into a NAND type gate with D going just into the NAND part of it that follows the NOR or the OR, and then a bubble at the end.